I've given you everything I wanted to give for the fermions in general. Now I have to do an example, a physical system where you can talk about the physics of the system in terms of Fermi-Dirac properties. It is white dwarf stars. Have you done this before, white dwarfs? Huh? No? Are you sure? You have never applied statistical mechanics to stars? Wow. So, okay, let's do a physical problem and see how the star is achieving its equilibrium size and mass. This also shows the wide range of physical problems you can use your statistical mechanics for. So, these stars are very special stars, very small sized, comparatively small sized. Let me write their properties, the most important properties. Small size stars, they are faint, abnormally faint, not bright, and of white color. You know what dwarf means? Yes. Okay. Faint color. Almost all hydrogen content used up. Thermonuclear reactions are proceedings. We are dealing with a star. So when the star burns the hydrogen, of course it goes to helium stage. So you mostly have helium in the star. H is, the star is mostly helium. Our sun is at the earlier stages of hydrogen burning. The sun is producing, our sun is producing helium, but thanks God that we have billions of years to finish up the hydrogen, go to the helium stage. It is mostly helium. This small brightness, little brightness, is coming from gravitational, slow gravitational contraction of the star. Okay? It is mainly from little brightness mostly from gravitational contraction. This is quite a slow contraction in these stars, and that's our main properties. Small size, faint color, mostly helium, and little brightness is coming mainly from gravitational contraction. Now let's model this as a problem. This is the important part because as I told you, statistical mechanics is model dependent. It depends on the model you establish for the physical problem at hand. The model, you can model this as follows. Let's look at the mass of the star. Mass is of the order of 10 to 33 grams. This is of helium, and that is approximately mass of our sun. This is the symbol for our sun. A circle and a dot at the center means sun, our sun, okay? So the stars have the mass of more or less like the mass of our sun. Well, density is high, so it is a smaller ball than the sun. Density is about 10 to 7 grams per centimeter cube, or so it is 10 billion times, 10 million times the density at our sun. It is denser than our sun. Let's look at the temperature of the star. Now, I think you will understand the importance of model making, creating the model for your system. The central temperatures of the order of 10 to 7 Kelvin. So this is corresponding to a mean thermal energy per particle, mean thermal energy per particle of the order of 1,000 electron volt. Okay. How do you go from temperature to energy? By multiplying with Boltzmann constant, isn't it? Kb times T is the corresponding energy. Okay. So what does that mean? It means that, well, it has a physical consequence. This simply means that all helium atoms are ionized. This is too much energy per particle. So the whole of helium completely ionized. That's what it means. Of course, you are good physics students, you know the physical consequence of a number, isn't it? You always look at numbers like that, I'm sure. Let's look at what is in the star, constituents of the star. Well, we have n electrons, and half this number helium nuclei, isn't it? Why half? Because there are 2 electrons per helium. Huh? Hydrogen has 1. Helium has 2. So if you have n electrons, you must have half of this nuclei, helium nuclei. Okay, so this is what we have. Now each of these helium nuclei has a mass of approximately 4 proton mass. Why? 2 protons, 2 neutrons. Electrons are very light, so you don't have to count them. So that's the mass. Therefore, mass of the star is approximately n times mass m2mp. N times electron mass, 2n times proton mass, more or less. So 2n mp. Let's look at the electron density. Number density is number of electrons per volume. So number m over the density of the star. So you have density of star divided by 2mp. This is of the order of approximately of the order of 10 to 30 electrons per centimeter cube. A lot of electrons per centimeter cube. Okay? Interesting. We are going step by step. Let's look at the Fermi momentum and Fermi energy, because we have to decide on the approximate temperature of the gas. Is this a degenerate gas, electron gas? Degenerate means at 0 temperature, 0 Kelvin. Okay, is it at 0 or at very high temperatures? What do you expect? Very high temperatures, the center of the star. It will turn out to be low temperatures. Let's see how we are going to decide. These steps are extremely important. I'm going step by step simply to show how to build a model for a system like this, for a star like this. Okay, let's continue with our model. Let's look at the Fermi momentum. Fermi momentum can be written as 3n over 8 pi. Drive this, if you like, times h. This is of the order of 10 to minus 17 grams centimeters per second. You can multiply these numbers and find the final result of the order of 10 to the minus 17. Well, if you look at m times c as characteristic momentum, of an electron, m times c, the reason is these are relativistic, aren't they? Highly energetic in the star. If you look at this, you can write Fermi energy as mc squared, that is rest energy of the electron. This is of the order of 1 million electron volt or 1 mega electron volt. Isn't it? 1 MeV. So you can look at this as temperature, corresponding temperature, which is the Fermi temperature, kBTF. That's the way you turn energy into temperature. You find a Fermi temperature of the order of 10 to 10 Kelvin. Oh, that's the most important result. Extremely important. So, to be able to say anything about the effective temperature of the electron gas, we have to know the Fermi temperature. We have to compare it with the Fermi temperature. It can be high, but if it is much lower than the Fermi temperature, we have a degenerate gas, don't we? A gas at zero temperature. Okay. Now, the result of this, the approximations that we can make to create our model. First, for the electrons are relativistic. So if you do a non-relativistic approximation, you should be able to know what you are doing, what type of an approximation you are doing. They are relativistic and it must be treated as a relativistic electron gas. Well, looking at TF and the effective temperature, what was it, 10 to the 7? Huh? What was electron effective temperature? 10 to the 7. So you have 1,000 times more for Fermi temperature. That means effectively your electron gas is at T equals 0. So statistically speaking, that means T is very much smaller than TF. Electron gas is at 0 Kelvin. Completely degenerate, almost. T over TF is of the order of 10 to the minus 3. Okay? Now, here is a famous model due to Chandrasekhar. Let's see what he did with that knowledge. Well, you can call this recent, quite Chandrasekhar. Chandrasekhar's model is appearing around 31 and 35. Most important contributions to this problem is made by this physicist. First approximation, helium nuclei is not going to contribute anything to dynamics. No contribution to dynamics. Why, do you know? Of this problem? Because they are heavy compared with the electrons. So they are not going to move much compared with the electrons. They are going to move, but not as fast as electrons. So the dynamics will be dominated by the electrons. So ignore them. In first approximation, you can include their contribution if you like later. Now you can neglect also one more thing. Neglect also the radiation effects. Radiation coming as a result of thermonuclear reactions at the center of the star, you can forget about that too. The effect of radiation. So what is left to model the star? The electron gas. So you have only the electron gas. Consider electron gas alone. Now I have given this step by step so that you might build your own model of physical systems. This is the most important thing a physicist can do. Instead of memorizing things, build the model. And you have to ask yourself the same questions when we discuss other problems. Isn't it? The photon gas, what are we doing? What are we taking into account and what are we omitting? We haven't taken interactions into account, for example, isn't it? So these are all models approaching to the reality. So if you calculate something using these models, you can say, well, in the first approximation, that's my result. If I am away from the experimental result, then I have to include something more. If I am coming close, I have taken all the important things into account, okay? So, that's the way you came up to the electron gas as modeling the faint white dwarf star. You can also assume one more thing in your model. Let's assume that electrons are distributed uniformly throughout the star. So may assume that the gas is uniform. Electron gas is uniformly distributed. So the density is the same everywhere in the star. So what is our problem then? We have reduced this problem into a very simple model. So to study a white dwarf star, we have to study the ground state properties of a degenerate, that means at t equals 0, degenerate Fermi gas or Fermi-Dirac gas of n relativistic electrons. That is our problem, isn't it? Let's do the thermodynamics of the star. My aim will be to look at the equilibrium condition, when the star will be in equilibrium. Okay? Before even doing this problem, we should remember there will be a Fermi pressure pushing the gas outward, isn't it? Because of Pauli exclusion principle, as we are discussing. And there will be a gravitational pull, collapse, if you like, because of attraction between particles. So these two things will keep the star in equilibrium. So Fermi pressure and gravitational attraction. So let's start, after all this model building, let's start the calculation of thermodynamic properties in this approximation, in this model. Okay. Now, since we are dealing with an electron gas, we know the degeneracy factor here is 2, 2s plus 1. S is 1/2, spin 1/2 for electrons. So the number of particles then, putting the constants in, writing the density of states. Why don't you check this way of writing it? At t equals 0, at absolute 0, all the states up to Fermi energy are filled by electrons, and nothing above the Fermi energy. They are all empty. So you can integrate up to the Fermi. So that gives you 8 pi v 3h cubed pf cubed, and pf 3n over 8 pi h. I have already used this. Do you remember? for the electron gas? Yeah. So let's look at the energy momentum relationship for a relativistic particle. Energy momentum. What is this? It is not E equals P squared over 2m, isn't it? It is non-relativistic. In the relativistic case, it is mc squared 1 plus P over mc squared square root minus 1. That's the relativistic energy of the particle. Well, the first term you remember is the c squared p squared plus m squared c to the 4 square root relativistic energy. You can get rid of the mass energy, rest mass energy, subtract that out, so that's it. Speed of particle is dE dP, that is P over M. So you should do everything relativistically. 1 plus P over MC squared 1/2 square root. M here is rest mass of electron. Now we can write the pressure for the gas. Because we are after pressure and gravitational pressure in some sense, coming from the potential energy. Let's call pressure of the gas P0. This pressure P0 can be written as 1/3 N over V, average value PU at 0. Check our earlier relationships that we have found. Pressure-energy relationship. So if you write this as an integral, this average value, it becomes 8 pi 3h cubed. Now integrals, of course, are a little bit more complicated than the easy ones. So these are just a few steps in the solution. I'm not going to do the whole mathematics step by step, although up to now I am doing it. Introduce a new variable, theta, by defining P momentum like this, so that the energy comes out to be C times tangent hyperbolic theta. So, therefore, you get the following result for the number of particles. 8 pi V m cube c cube 3h cube sinus hyperbolic cube theta f. You can write this as follows. This constant times x cubed. Sinus hyperbolic theta f is x. So that the pressure can be calculated as 8 pi m to the 4 c to the 5 3h cubed 0 to theta Fermi sinus hyperbolic 4 theta d theta. Well, that's the complication that comes from relativistic problem. You can write this in terms of a function pi m4c to the 5 function a of x and this a of x is the following function, x squared plus 1 to the power 1/2, that is square root, 2x squared minus 3 plus 3 sinus hyperbolic x inverse. That's the function that comes from that integral. And of course, we called x sinus hyperbolic theta f. When you look at the expression, you can see it. It's the same thing. Just this thing is called x. Now you can compute this for any x, but you can also look at the limiting forms of this function. You can write this function in two limits for small x and large x as follows. For small x, this turns into 8 over 5 x to the 5 minus x to the 7, 1/3 x to the 9 minus 5 22 x to 11. See, if x is small, the terms are getting smaller and smaller rapidly, higher order terms. So you don't have to keep going for very small x, that's the result. Of course, for large x, it must be something different. 2x4 minus 2x squared plus 3 ln x minus 7 over 12 plus 5 over 4 x minus 2 etc. for large x. So higher order terms from here on will be smaller and smaller. Okay? So we know everything about the function. We know pressure, in other words. To get the equilibrium, we also, instead of only concentrating on the pressure coming from the electrons, because they are fermions, you have to think about the gravitational contraction too. Let's look at that problem. So we can establish an equilibrium by looking at the gravitational part of the model. Gas will exert pressure P0N on the walls Well, if you think about external walls, so we don't have the walls. If you put this into a cup, if you like, imaginary, that's the pressure coming from the electron gas. Well, assuming spherical configuration, this adiabatic change in volume, of course, when you apply pressure, there is a change in volume. This change can be related to a change in the energy of the gas. The pressure is from in to out, so it is an increase in volume. What does that mean? A gas, expanding gas lowers the temperature, isn't it? There's a change in energy. P0 and V, so it is minus P0 at radius R of this sphere corresponding to the star, 4 pi R squared dr is the volume element. PdV is the corresponding change in energy for the pressure we are talking about. Okay? So we have to compare this with the gravitational. We have the expression, exact expression for P0 in terms of AX. So we can look at that in detail. Now we have to look at the effect of gravitation that is causing the opposite motion, which is contraction. Expansion is meeting with contraction, so equilibrium will be established. Change in potential energy in this case is, what is the potential energy? Gravitational potential is minus gm squared over r, isn't it? A spherical shape. So dEg dr is gm squared over r squared. Take the derivative. Is that okay? So this gives a dE, which is some constants, gm squared r squared times dr. This is of the order of 1, so, okay? We have gravitational change in energy. We have a change in energy as a result of outward pressure coming from the gas. So we can get the equilibrium. When you add these two changes, they should add to 0, isn't it? That's the equilibrium. We have finally reached it, but we are 5 minutes off. Let me stop at this point. So, equilibrium dE0 plus dEg is 0. That will give us a condition on the star. When do we have this equilibrium? And especially we have to refer mass to radius to get the meaning of that condition. I will do it soon. So if you want to see your exam paper, you can come again. I will give you a homework paper, okay?